Picture a moment so profound that it set the stage for everything you know, every star, every planet, every breath you take. That moment was the birth of the universe, a spark that ignited the cosmos as we know it. Today, we're diving into one of the greatest mysteries of all time, the Big Bang and cosmic inflation. These aren't just scientific theories, they're the keys to understanding how our universe began, how it grew, and why it looks the way it does today. From the tiniest particles to the vastness of space, these discoveries have reshaped our understanding of existence itself. In this video, we'll uncover 25 incredible revelations that have transformed how we see the Big Bang and cosmic inflation, taking you on a journey through time, space, and the very fabric of reality. Stay with us as we explore the secrets of the universe's earliest moments. You're about to witness discoveries so mind-blowing, they'll make you see the cosmos in a whole new light. Ready to begin? Let's dive in. Now, let's take a step back in time to one of the most groundbreaking discoveries in cosmology, the cosmic microwave background, or CMB. This discovery, made in 1965, is often referred to as the afterglow of the Big Bang, and for good reason. It's essentially the oldest light in the universe, a faint whisper from its very beginnings. Scientists Arno Penzias and Robert Wilson stumbled upon this cosmic relic while working with a radio antenna designed to study signals from space. What they found wasn't just random noise, but a uniform glow of microwave radiation that filled the entire sky. This wasn't just any radiation, it was a direct look back in time, a snapshot of the universe when it was just 380,000 years old. The CMB's remarkable uniformity tells us that the early universe was an incredibly smooth and consistent place, though tiny fluctuations in this background radiation would later seed the formation of galaxies and stars. Think of it as a cosmic fingerprint, a permanent record of the universe's infancy, and one of the strongest pieces of evidence we have for the Big Bang theory. It's a discovery that didn't just confirm a theory, it opened a window into the first moments of existence itself. Moving forward in our exploration of the Big Bang's incredible discoveries, let's turn our attention to something seemingly simple yet profoundly significant: the abundance of helium in the universe. The Big Bang theory didn't just explain the origin of everything we see today. It also made precise predictions about the elements that would form in its aftermath. One of the most remarkable predictions was the amount of helium that would exist in the cosmos. According to the theory, during the first few minutes after the Big Bang, conditions were just right for nuclear fusion to occur, creating helium from the primordial hydrogen that filled the universe. The math suggested that about 25% of the universe's matter would be helium, with the rest primarily hydrogen. For decades, this prediction seemed almost too bold, but when scientists began measuring the helium content in stars, galaxies, and even interstellar gas, they found something astounding. The numbers matched almost exactly. This discovery wasn't just a lucky guess, it was a direct validation of the Big Bang theory. The precise helium abundance we observe today serves as a cosmic time capsule, a remnant of the universe's earliest moments. It's a piece of evidence that not only supports the Big Bang, but also helps us understand the processes that shaped the cosmos in its infancy. This discovery reminds us that even the simplest elements can hold the key to unlocking the universe's greatest mysteries. Shifting our gaze to the vast expanse of the cosmos, we encounter one of the most groundbreaking discoveries in modern astronomy, the Hubble expansion. In the 1920s, astronomer Edwin Hubble made an observation that would forever change our understanding of the universe. By studying the light from distant galaxies, Hubble noticed something extraordinary. These galaxies were moving away from us, and the farther they were, the faster they seemed to be receding. This pattern, now known as Hubble's law, pointed to a startling conclusion: the universe itself was expanding. At the time, this idea was revolutionary. It challenged the prevailing notion of a static, unchanging universe and opened the door to a new way of thinking about cosmic origins. Hubble's discovery provided a crucial piece of evidence for the Big Bang theory. If the universe is expanding today, it stands to reason that it must have been much smaller and denser in the past. Rewind the cosmic clock far enough, and everything we see today would have been compressed into an incredibly hot, dense point, the very essence of the Big Bang. This expansion doesn't just explain the movement of galaxies, it also helps us understand the universe's age, size, and ultimate fate. Hubble's work laid the foundation for modern cosmology, showing us that the cosmos is not static but dynamic, constantly evolving from that initial burst of creation. It's a humbling reminder that the universe is still unfolding, carrying the echoes of its explosive birth in every corner of space. Now, let's turn our attention to a puzzle that has puzzled cosmologists: the flatness problem. When scientists began studying the geometry of the universe, they made a surprising observation. On a large scale, the universe appears to be flat. This isn't the flatness we think of in everyday terms, like a sheet of paper, but rather a precise mathematical flatness in the fabric of space-time. According to Einstein's theory of general relativity, the universe's geometry could take one of three forms: positively curved like a sphere, negatively curved like a saddle, or perfectly flat. The discovery that we live in a flat universe was unexpected because it required an extraordinary level of fine-tuning in the early universe. For the universe to remain flat over billions of years, the density of matter and energy at the time of the Big Bang had to be incredibly precise, so precise that even the tiniest deviation would have caused the universe to either collapse in on itself or expand too rapidly to form the structures we see today. This fine-tuning seemed too improbable to be a coincidence, leading scientists to question the initial models of the Big Bang. Enter cosmic inflation, a theory proposed by physicist Alan Guth in the early 1980s. Inflation suggests that in the first tiny fraction of a second after the Big Bang, the universe underwent an exponential expansion, stretching space-time to an enormous degree. This rapid expansion would have smoothed out any curvature, explaining why the universe appears flat today. Inflation not only solves the flatness problem, but also provides a mechanism for the universe's uniformity on a grand scale. It's a powerful idea that has reshaped our understanding of the cosmos, offering a compelling explanation for one of the universe's most puzzling features. With this in mind, we can see how inflation acts as a bridge, connecting the mysteries of the early universe to the observable cosmos we study today. Now let's dive into another fascinating puzzle, the horizon problem. Imagine looking at two distant regions of the universe, billions of light years apart. Despite their immense separation, these regions share the same temperature. This might not seem strange at first glance, but here's the catch. These areas are so far apart that light, and therefore heat, hasn't had enough time to travel between them since the Big Bang. In other words, they've never been in contact with each other. So why do they share the same temperature? This mystery baffled scientists for decades, as it seemed to defy the laws of physics. According to our understanding of the universe's early moments, there simply wasn't enough time for these regions to exchange energy and reach thermal equilibrium. This is where cosmic inflation comes to the rescue once again. Inflation proposes that in the first fraction of a second after the Big Bang, the universe expanded at an astonishing rate, much faster than the speed of light. This rapid expansion would have stretched a tiny, uniform region of space across the entire observable universe, ensuring that all parts of the cosmos started with the same conditions, including temperature. As the universe continued to expand, these regions moved apart but retained their original uniformity. Inflation elegantly explains the horizon problem, showing how distant parts of the universe could share the same temperature without ever interacting. It's yet another way this groundbreaking theory has helped us understand the universe's earliest moments. And with that, we begin to see how inflation ties together so many of the universe's most puzzling features. Moving forward, let's explore one of the most revolutionary ideas in cosmology, the discovery of cosmic inflation. In the late 1970s, physicist Alan Guth proposed a groundbreaking theory to address some of the universe's biggest mysteries. He suggested that in the first fraction of a second after the Big Bang, the universe underwent an extraordinary period of rapid expansion. This wasn't just any expansion, it was exponentially faster than anything we observe today, stretching space itself at speeds far beyond the speed of light. What makes this theory so remarkable is how it elegantly solves several cosmological puzzles, like the horizon problem we just discussed. Guth's idea wasn't just a minor adjustment to the Big Bang theory, it was a complete game changer. It provided a mechanism for how the universe could have grown from a tiny, uniform region into the vast, complex cosmos we see today. Inflation also explains why the universe appears so flat and why distant regions share the same temperature, even though they've never interacted. But perhaps its most profound implication is how it connects the tiniest scales of quantum mechanics to the largest scales of the cosmos. During inflation, minuscule quantum fluctuations were stretched to cosmic proportions, eventually becoming the seeds for galaxies, stars, and planets. This discovery didn't just fill gaps in our understanding, it reshaped the entire field of cosmology, giving scientists a new framework to explore the universe's origins. Today, cosmic inflation remains one of the most widely accepted theories in modern physics, and its implications continue to inspire new research and discoveries. As we'll see in the next section, this theory also paves the way for understanding how quantum mechanics played a role in shaping the early universe. Stepping into the fascinating realm of the early universe, let's uncover how the smallest ripples gave rise to everything we see today. During the brief but explosive period of cosmic inflation, the universe wasn't perfectly smooth. Instead, it was filled with tiny quantum fluctuations, microscopic variations in energy that were, at their core, the result of quantum mechanics at work. These fluctuations were so small that they might seem insignificant, but inflation did something extraordinary. It stretched them to cosmic scales. As the universe expanded exponentially, these tiny irregularities were magnified, creating slight differences in density across space. These density variations became the building blocks for the large-scale structure of the universe. Over billions of years, gravity pulled matter together in regions where it was slightly denser, forming the first clumps of matter. These clumps grew into galaxies, galaxy clusters, and the vast cosmic web we observe today. What's truly astonishing is that the seeds of this structure, the very fabric of the cosmos, originated from quantum fluctuations so small they're almost unimaginable. This discovery not only links the quantum world to the cosmic scale, but also explains why the universe isn't uniform. Instead, it's filled with galaxies, stars, and planets, all tracing their origins back to those minuscule ripples during inflation. As we'll explore next, these quantum fluctuations also played a pivotal role in shaping the cosmic microwave background, offering us a glimpse into the universe's earliest moments. Moving forward in our exploration of cosmic inflation, we encounter a moment that both captivated and challenged the scientific community. In 2014, the BICEP-2 experiment announced a groundbreaking discovery. They claimed to have detected gravitational waves from the early universe, specifically from the era of cosmic inflation. This detection was seen as a potential smoking gun for inflation, as it would provide direct evidence of the rapid expansion predicted by the theory. The excitement was palpable, with many declaring it one of the most important finds in modern cosmology. However, the story took an unexpected turn. Further analysis revealed that the detected signal could have been caused by cosmic dust in our own galaxy, rather than primordial gravitational waves. This realization led to the retraction of the initial claim, sparking a mix of disappointment and renewed determination within the field. While the Bicep 2 controversy was a setback, it also underscored the importance of rigorous scientific scrutiny. It reminded researchers of the complexities involved in studying the universe's origins and the need for multiple lines of evidence to confirm such profound discoveries. This episode wasn't a failure but a learning moment, driving the development of more precise instruments and methods to continue the search for gravitational waves from inflation. As we'll see next, advancements like the Planck satellite have since provided even clearer insights into the Big Bang's afterglow, pushing the boundaries of our cosmic understanding even further. Shifting our focus to more definitive breakthroughs, the Planck satellite stands as a monumental achievement in cosmology. Launched in 2009 by the European Space Agency, this mission was designed to map the cosmic microwave background, or CMB, with unprecedented precision. Over its operational lifetime, Planck collected data that allowed scientists to refine our understanding of the early universe like never before. The satellite's measurements revealed the CMB's temperature fluctuations in extraordinary detail, offering a high-resolution map of the universe's infancy. These fluctuations, often referred to as the seeds of cosmic structure, provided critical insights into the conditions that existed during the Big Bang and the subsequent period of cosmic inflation. One of Planck's most significant contributions was its ability to test and validate key predictions of the inflation theory. For instance, it confirmed the universe's flat geometry with remarkable accuracy, aligning with inflation's expectations. Additionally, Planck's data helped narrow down the timeline for inflation, suggesting that it occurred within the first tiny fraction of a second after the Big Bang. The mission also shed light on the composition of the universe, refining estimates of dark matter and dark energy. By providing the most precise measurements of the CMB to date, Planck not only reinforced the foundations of the Big Bang theory, but also set a new benchmark for cosmological research. Its legacy continues to shape our quest to unravel the universe's deepest mysteries, proving that even in the face of challenges, precision and persistence lead to profound discoveries. Moving forward, let's explore one of the most groundbreaking revelations in modern cosmology, the discovery of dark energy. This mysterious force first came to light in the late 1990s when astronomers made a startling observation. They found that the universe wasn't just expanding, it was accelerating in its expansion. This discovery was made by studying distant supernovae, which served as cosmic mile markers. What they revealed was that galaxies were moving away from each other at an ever-increasing speed, a phenomenon that defied expectations. This acceleration couldn't be explained by gravity alone, which typically pulls objects together rather than pushing them apart. Scientists realized that an unknown energy must be driving this expansion, and they named it dark energy. Dark energy is now believed to make up around 68% of the universe's total energy content, dwarfing the contributions of both matter and dark matter. Its existence has profound implications for the Big Bang theory, as it helps explain the universe's evolution after its initial explosion. In the aftermath of the Big Bang, dark energy may have played a crucial role in shaping the cosmos we see today. It's thought to be responsible for the universe's current large-scale structure, influencing the distribution of galaxies and cosmic voids. Yet, despite its significance, dark energy remains one of the greatest mysteries in science. We don't yet know what it is or how it works, but its discovery has fundamentally altered our understanding of the universe's fate. As we continue to probe this enigma, one thing is certain: dark energy is a key piece of the puzzle that connects the Big Bang to the cosmos we inhabit today. Now, let's journey further back in time to uncover another pivotal chapter in the universe's story, the era of the first stars and reionization. After the Big Bang, the universe was a dark, dense soup of gas, mostly hydrogen and helium. For hundreds of millions of years, no stars or galaxies existed. But then, something extraordinary happened. gravity began to pull together pockets of gas, compressing them until they ignited, giving birth to the very first stars. These stars were unlike anything we see today, massive, hot, and short-lived. Their intense ultraviolet light began to ionize the surrounding hydrogen gas, stripping electrons from atoms in a process known as reionization. This marked a transformative phase in the universe's history, turning it from a neutral state to one filled with charged particles. The light from these first stars traveled far and wide, essentially lighting up the cosmos for the first time. This period of reionization didn't happen all at once. It unfolded over hundreds of millions of years, gradually changing the universe's structure. The implications of this era are profound. It helps us understand how the universe evolved from its initial, hot, dense state to the complex web of galaxies and stars we observe today. Reionization also provides crucial insights into the timeline of the Big Bang, filling in gaps about how the universe transitioned from darkness to light. It's a reminder of how interconnected these cosmic events are, each one building on the last to shape the universe we call home. Turning our attention to the very fabric of the universe, let's explore the abundance of light elements, a cornerstone of the Big Bang theory. In the first few minutes after the Big Bang, the universe was a seething cauldron of energy and particles. As it cooled, the conditions became just right for the formation of the simplest atomic nuclei: hydrogen, helium, and a trace amount of lithium. These elements weren't forged in stars but were created in a process known as Big Bang nucleosynthesis. The beauty of this theory lies in its precision. Scientists calculated the ratios of these elements based on the conditions of the early universe, and remarkably, observations matched those predictions almost perfectly. Hydrogen, the simplest and most abundant element, makes up roughly 75% of the universe's elemental content. Helium, the second most abundant, accounts for about 25%. Lithium, though far less abundant, exists in just the tiny amounts predicted. This alignment between theory and observation is one of the strongest pieces of evidence supporting the Big Bang. It's a testament to the power of physics and our ability to trace the universe's history back to its earliest moments. The abundance of these light elements not only confirms the Big Bang, but also provides a foundation for understanding the chemical evolution of the cosmos, setting the stage for the formation of stars, galaxies, and ultimately, life itself. Building on the remarkable story of the universe's earliest elements, we now step into the era known as the epoch of nucleosynthesis. This short but profoundly significant period occurred just minutes after the Big Bang, when the universe had cooled enough for the first atomic nuclei to form. Picture this: an unimaginably hot and dense cosmos still in its infancy, filled with a chaotic mix of protons, neutrons, and energy. As the universe expanded and cooled, the conditions became perfect for these particles to collide and combine. Protons and neutrons fused together, creating the very first atomic nuclei, primarily hydrogen and helium, with a tiny fraction of lithium. This process, known as nucleosynthesis, wasn't random. It was governed by the precise laws of physics, dictating how much of each element could form. What's fascinating is how brief this window of opportunity was. Lasting only a few minutes, nucleosynthesis set the stage for the chemical composition of the universe we see today. Without this critical phase, the cosmos would lack the building blocks necessary for stars, planets, and life itself. It's a humbling reminder of how finely tuned the early universe was, and how even the smallest changes could have led to a completely different cosmic story. The epoch of nucleosynthesis isn't just a moment in history, it's the foundation of everything that followed. Now, let's turn our attention to one of the most fundamental questions in cosmology. How old is the universe? Determining the age of the cosmos might seem like an impossible task, but thanks to groundbreaking discoveries and precise measurements, scientists have been able to unlock this mystery. The key lies in two critical pieces of evidence: the cosmic microwave background and Hubble's constant. The cosmic microwave background, or CMB, is like a time capsule from the universe's infancy, offering a snapshot of its earliest moments. By analyzing this faint radiation, astronomers can calculate the rate at which the universe has been expanding since the Big Bang. Meanwhile, Hubble's constant measures the current rate of this expansion, using observations of distant galaxies moving away from us. When these two data points are combined, they allow researchers to trace the universe's growth backward in time, arriving at the moment it all began. The result: the universe is estimated to be approximately 13.8 billion years old. This number isn't just a figure. It's a testament to the precision of modern cosmology and our ability to piece together the story of the cosmos. It's also a reminder of how far we've come in our understanding of the universe's origins, from a time when such questions seemed unanswerable to now, when we can confidently say we know the age of everything around us. This discovery not only deepens our appreciation of the universe's history, but also serves as a foundation for countless other scientific inquiries into its nature and evolution. Building on our journey through the universe's earliest moments, let's now explore one of the most elusive remnants of the Big Bang, the cosmic neutrino background. Just as the cosmic microwave background gives us a glimpse of the universe's infancy, neutrinos, those nearly massless, ghostly particles, offer another window into the cosmos's very first seconds. Neutrinos were created in abundance during the Big Bang, flooding the universe with trillions upon trillions of these particles. Unlike photons, which make up the CMB, neutrinos are incredibly difficult to detect because they interact so weakly with matter. This makes them a cosmic mystery waiting to be unraveled. Scientists believe that these primordial neutrinos still permeate the universe today, forming a cosmic neutrino background that could hold vital clues about the conditions of the early universe. Detecting this background is one of the most challenging tasks in modern physics, but experiments like the IceCube Neutrino Observatory and future projects aim to capture even the faintest traces of these particles. Discovering the cosmic neutrino background would not only confirm a key prediction of the Big Bang theory, but also provide insights into how the universe cooled and expanded in its earliest moments. It's a reminder that even the smallest particles can carry the biggest secrets about our cosmic origins. Shifting our focus to one of the most intriguing ideas in modern cosmology, let's dive into the multiverse hypothesis. Cosmic inflation, the rapid expansion of the universe in its earliest moments, doesn't just explain the structure of our observable universe, it also opens the door to the possibility of countless other universes existing beyond our own. According to this theory, inflation may not have been a one-time event but rather a process that continues in other regions of space-time, creating bubble universes with their own physical laws and constants. These universes could be vastly different from ours, some perhaps even with dimensions or forces we can't begin to imagine. While the multiverse hypothesis is compelling, it's also highly controversial. Critics argue that it's untestable by nature, as we can't observe or interact with these other universes. However, proponents suggest that indirect evidence, such as anomalies in the cosmic microwave background or the fine-tuning of our universe's constants, could hint at the presence of a multiverse. This idea challenges not only our understanding of the cosmos but also the very nature of existence itself. Whether or not the multiverse is real, it pushes the boundaries of science and philosophy, inviting us to think bigger than ever before. With ongoing research and new technologies, this cosmic mystery remains one of the most fascinating topics in the quest to understand our place in the universe. Turning now to another profound cosmic mystery, let's explore the discovery of dark matter. While the Big Bang set the stage for the universe's expansion, it was the presence of dark matter that played a crucial role in shaping the cosmos as we know it. In the 1930s, astronomer Fritz Zwicky observed that galaxies in the Coma cluster were moving much faster than expected based on the visible matter alone. This discrepancy hinted at the existence of an invisible gravitational force holding these galaxies together, dark matter. Later, in the 1970s, Vera Rubin's study of galaxy rotation curves provided even stronger evidence. She found that stars at the edges of galaxies orbited at similar speeds to those near the center, defying the laws of gravity unless vast amounts of unseen matter were present. Dark matter doesn't emit, absorb, or reflect light, making it invisible to telescopes. Yet, its gravitational effects are undeniable, bending light from distant objects in a phenomenon called gravitational lensing. This unseen substance makes up roughly 27% of the universe's total mass and energy, far outweighing ordinary matter. Without dark matter, galaxies and large-scale structures wouldn't have formed after the Big Bang. Its presence is a testament to the universe's hidden complexity, reminding us that much of what shapes our cosmos remains shrouded in mystery. As scientists continue to search for dark matter particles, this elusive substance stands as one of the most compelling puzzles in modern cosmology. Now, let's shift our focus to a monumental milestone in cosmic history, the formation of the first galaxies. After the Big Bang and the era of cosmic inflation, the universe was a vast, dark expanse filled with a sparse soup of hydrogen and helium. But within this primordial chaos, the seeds of galaxies were already taking root. Tiny quantum fluctuations during inflation created slight variations in density across the universe. These fluctuations, initially minuscule, grew over time as gravity pulled matter together. By about 200 million years after the Big Bang, the first stars began to ignite, illuminating the cosmic darkness. These early stars gathered into dense clusters, forming the first protogalaxies. Over hundreds of millions of years, these protogalaxies merged and grew, driven by gravity's relentless pull. The result was the birth of the first true galaxies, vast collections of stars, gas, and dark matter. These galaxies were much smaller and denser than those we see today, but they laid the foundation for the large-scale structure of the universe. Observations from telescopes like the Hubble Space Telescope and the James Webb Space Telescope have allowed scientists to peer back in time, capturing light from these ancient galaxies. What they've found is astonishing. Even in its infancy, the universe was already bustling with activity, forming structures that would eventually evolve into the galaxies we know today. The first galaxies are a testament to the enduring influence of cosmic inflation, proving that the universe's earliest moments set the stage for the incredible complexity we see around us. As we continue to explore these distant cosmic beacons, we gain deeper insights into how our universe came to be, a story written in the stars. Now, let's turn our attention to one of the most fascinating questions in cosmology. What brought cosmic inflation to an end? For a fraction of a second after the Big Bang, the universe expanded at an unimaginable rate, driven by a mysterious force known as inflation. But this rapid expansion couldn't last forever. Scientists believe that inflation ended when the energy field responsible for it decayed, releasing its stored energy in a process called reheating. This energy transformed into the intense heat and particles that filled the early universe, marking the beginning of what we now call the hot Big Bang. Think of it like a balloon that's been stretched to its limit. Once the air is released, it settles into a new state. Similarly, the end of inflation set the stage for the universe to cool and evolve into the cosmos we see today. Theories suggest that inflation may have ended unevenly, creating slight variations in temperature and density across the universe. These variations, imprinted during inflation, became the seeds for galaxies and cosmic structures. The transition from inflation to the Big Bang's hot, dense state is a critical moment in cosmic history as it shaped everything that followed. While the exact mechanisms remain a topic of intense research, the end of inflation marked the beginning of a new chapter in the universe's story, one filled with light, matter, and the building blocks of everything we know. Moving deeper into the origins of our universe, we come face to face with one of the most perplexing concepts in all of cosmology, the singularity of the Big Bang. This singularity represents the very beginning, a moment when all the matter, energy, space, and time we know today were compressed into an infinitely dense and infinitely small point. Imagine trying to pack the entire universe into a space smaller than the tip of a needle. This is the scale we're talking about. But here's the catch: our current laws of physics, including Einstein's theory of relativity, break down when we try to describe such extreme conditions. Gravity becomes so intense that it warps space and time beyond comprehension, and the familiar rules of quantum mechanics seem to lose their footing. This is why the singularity remains one of the greatest mysteries in science. It's like trying to read a book with half the pages missing. Some scientists believe that understanding the singularity requires a new framework, perhaps a theory of quantum gravity that unifies the forces of nature. Others suggest that the singularity might not even be a physical reality, but rather a sign that our mathematical models are incomplete. What we do know is that this moment set the stage for everything that followed, from the rapid expansion of the universe to the formation of galaxies and stars. The singularity is a reminder that even with all we've discovered, the universe still holds secrets that challenge our understanding of existence itself. And as we continue to probe its mysteries, we may uncover clues that reshape not just our view of the Big Bang, but our very place in the cosmos. Shifting our focus to a groundbreaking achievement in modern science, we arrive at the discovery of gravitational waves in 2015. These ripples in the fabric of space-time, first predicted by Albert Einstein a century earlier, were finally detected by the Laser Interferometer Gravitational Wave Observatory, or LIGO. This monumental discovery confirmed a key piece of Einstein's theory of general relativity and opened a new window into the universe. Gravitational waves are generated by cataclysmic events, such as the collision of black holes or neutron stars, which send shockwaves through space-time itself. But what makes this discovery so significant for our understanding of the Big Bang and cosmic inflation? Gravitational waves from the early universe could carry imprints of the rapid expansion that occurred just fractions of a second after the Big Bang. These signals, if detected, would provide direct evidence of inflation and offer a glimpse into the universe's earliest moments. While the waves detected so far originate from more recent cosmic events, scientists are actively searching for the faint, primordial waves that could trace back to the birth of the cosmos. This discovery not only validates a century-old prediction, but also paves the way for unlocking some of the universe's oldest secrets. With each detection, we inch closer to understanding how it all began. Now, let's take a closer look at one of the most fascinating aspects of the Big Bang: the role of quantum mechanics in the universe's earliest moments. Quantum mechanics, the science of the very small, might seem unrelated to the vastness of the cosmos, but it's actually essential to understanding how everything began. In the first fraction of a second after the Big Bang, the universe was unimaginably tiny, smaller than an atom. At this scale, the rules of classical physics break down and quantum mechanics takes over. Tiny fluctuations at the quantum level played a critical role in shaping the universe as we know it today. These random, microscopic ripples in the fabric of space-time became the seeds for all the cosmic structures we see, from galaxies to galaxy clusters. Without quantum mechanics, the universe would have been smooth and uniform, lacking the rich diversity of structures that make it so dynamic. What's even more astonishing is that these quantum fluctuations were stretched and amplified during cosmic inflation, embedding themselves into the very fabric of the cosmos. This means that the patterns we observe in the cosmic microwave background, the faint afterglow of the Big Bang, are direct imprints of these quantum events. So, when we look at the universe today, we're essentially seeing the effects of quantum mechanics on a cosmic scale. This connection between the smallest and the largest realms of existence is one of the most profound insights of modern cosmology, showing how deeply interconnected the laws of physics are. As we continue to explore the universe's origins, quantum mechanics remains a vital piece of the puzzle, helping us unravel the mysteries of how it all began. Now, let's shift our gaze to another remarkable feature of the cosmos, the discovery of cosmic voids. These vast, seemingly empty regions of space are as fascinating as they are mysterious. Imagine the universe not as a uniform expanse but as a cosmic web, with dense clusters of galaxies interconnected by filaments and separated by enormous voids. These voids, some stretching hundreds of millions of light years across, are not just empty space in the traditional sense. Instead, they are regions where matter is significantly sparser compared to the rest of the universe. But how did these voids form? It all traces back to the early moments of the Big Bang. During cosmic inflation, tiny quantum fluctuations were stretched to enormous scales. As the universe expanded and cooled, these fluctuations influenced the distribution of matter. Denser regions became the seeds for galaxies and galaxy clusters, while the less dense areas evolved into these vast voids. Over billions of years, gravity pulled matter from these underdense regions into the denser ones, further accentuating the contrast between the web of galaxies and the emptiness of the voids. What makes cosmic voids so intriguing is that they are not just passive features but active players in the cosmic story. For instance, the emptiness of these regions affects the way light travels through the universe, bending and distorting it in ways that help us map the distribution of dark matter. They also serve as natural laboratories for testing theories about the universe's expansion and the nature of dark energy. In essence, cosmic voids are a testament to the intricate balance of forces that shaped our universe, revealing how even the emptiest parts of space hold profound insights into the cosmos's origins and evolution. As we continue to explore these seemingly barren regions, we uncover more about the grand tapestry of the universe and the forces that wove it together. Now, let's turn our attention to one of the most profound questions in cosmology. What lies ahead for the universe? The fate of the cosmos is deeply tied to its origins in the Big Bang, and scientists have proposed several compelling theories about how it all might end. One of the most widely discussed scenarios is the heat death of the universe. In this model, the universe continues to expand indefinitely, driven by dark energy. Over trillions of years, stars will exhaust their fuel, galaxies will drift apart, and all matter will decay into its most basic components. Eventually, the universe will reach a state of maximum entropy, where no usable energy remains, and it becomes a cold, dark, and lifeless expanse. This bleak but scientifically grounded vision is often called the Big Freeze. On the other hand, some theories suggest a more dramatic conclusion, the Big Crunch. If dark energy's influence weakens over time, gravity could eventually reverse the universe's expansion, pulling everything back together. Galaxies would collide, temperatures would rise, and the cosmos would collapse into a hot, dense state, a mirror image of the Big Bang itself. This cyclical model implies that the universe could experience an endless series of expansions and contractions, with each cycle beginning anew. There's also the intriguing possibility of the Big Rip, where dark energy's strength increases over time, tearing apart galaxies, stars, and even atoms in a catastrophic final act. Each of these theories tells a different story about the universe's ultimate fate, but they all stem from our understanding of the Big Bang and the forces that have shaped the cosmos ever since. As we ponder these possibilities, we're reminded that the universe's future is as mysterious and awe-inspiring as its origins. The same forces that set the cosmos in motion billions of years ago continue to shape its destiny, inviting us to explore the profound connections between the beginning, the present, and the end of everything. As we shift our gaze from the distant future, Let's look back to the very beginnings of the cosmos with one of humanity's most remarkable tools, the James Webb Space Telescope. Since its launch, this extraordinary observatory has been rewriting our understanding of the early universe, offering unprecedented glimpses into the moments following the Big Bang. Equipped with its advanced infrared capabilities, the James Webb Space Telescope can peer through cosmic dust and observe light from the first galaxies that formed over 13 billion years ago. These observations are providing critical tests for theories of cosmic inflation and the Big Bang itself. For instance, by studying the faint glow of these ancient galaxies, scientists can better understand how the universe expanded and evolved in its infancy. The telescope has also been instrumental in refining measurements of the cosmic microwave background, the faint afterglow of the Big Bang, offering new insights into the conditions that shaped the cosmos. Moreover, the James Webb Space Telescope has discovered evidence of early star formation and the reionization era, a pivotal period when the first stars and galaxies lit up the universe, ending the so-called cosmic dark ages. These findings are not just filling in gaps in our knowledge, they're challenging and refining our understanding of the Big Bang and the forces that drove the universe's rapid expansion. As the James Webb Space Telescope continues to explore the cosmos, it promises to unlock even more secrets about the universe's origins, bringing us closer than ever to answering the profound questions of how it all began. Shifting our perspective from the scientific to the philosophical, the Big Bang Theory doesn't just explain how the universe began, it profoundly reshapes our understanding of existence itself. For centuries, humans have grappled with questions about where we came from and why we're here. The Big Bang offers a framework that moves beyond myth and speculation, grounding these questions in observable science. It challenges the notion of a static, eternal universe, instead presenting a dynamic, ever-evolving cosmos with a definitive beginning. This raises profound questions about the nature of time, space, and even the concept of nothingness. If the universe had a starting point, what existed before? Can we even speak of a before if time itself began with the Big Bang? These ideas push the boundaries of human thought, inviting us to reconsider our place in the grand tapestry of existence. Moreover, the theory's implications for the multiverse, suggesting that our universe might be just one of many, expand the philosophical debate even further. It forces us to confront the possibility that we are not the center of everything, but rather one small part of an unimaginably vast reality. The Big Bang also invites reflection on the fine-tuning of the universe. Why do the laws of physics allow for the existence of galaxies, stars, and life? Is this a product of chance, necessity, or something beyond our understanding? These questions don't just belong to scientists, they resonate with anyone who has ever looked up at the night sky and wondered. As we continue to explore the Big Bang's mysteries, we're not just uncovering the history of the cosmos, we're also exploring the very essence of what it means to be alive in a universe that is both vast and fleeting. Turning our attention to the tools that enable these profound discoveries, mathematics stands as the unsung hero of cosmology. Without its precise language, the complex theories of the Big Bang and cosmic inflation would remain abstract ideas rather than testable science. Mathematics provides the framework that allows us to translate the chaos of the early universe into orderly equations, offering predictions that can be compared with real-world observations. Take, for example, the equations of general relativity, which Albert Einstein formulated in the early 20th century. These equations not only describe how massive objects warp spacetime, but also laid the groundwork for understanding the universe's expansion. When Edwin Hubble observed galaxies moving away from each other, it was mathematics that connected his findings to the Big Bang theory, showing that the universe was not static but dynamic. Similarly, the theory of cosmic inflation proposed by Alan Guth relies heavily on mathematical models to explain how the universe expanded exponentially in its first moments. These models predict specific patterns in the cosmic microwave background, which have been confirmed by missions like the Planck satellite. Mathematics also allows cosmologists to explore scenarios that are impossible to observe directly, such as the conditions of the universe in its first fraction of a second. Through simulations and calculations, scientists can test hypotheses about the universe's shape, composition, and ultimate fate. Yet, mathematics in cosmology is not just about solving equations, it's about uncovering the hidden patterns and symmetries that govern the cosmos. From the intricate dance of particles during nucleosynthesis to the vast web of galaxies shaped by dark matter, mathematics reveals the underlying order of the universe. It's a reminder that, even in the face of the unknown, there is a language that helps us make sense of it all. As we continue to push the boundaries of our understanding, mathematics will remain an essential tool, guiding us toward new insights into the origins and evolution of the cosmos. Looking ahead, the quest to unravel the mysteries of cosmic inflation and the Big Bang continues to inspire groundbreaking missions and innovative technologies. One of the most anticipated projects is the launch of next-generation space telescopes, such as the LightBird mission, which aims to map the cosmic microwave background with unprecedented precision. By capturing even finer details of this ancient light, scientists hope to uncover subtle imprints left by inflation, offering new clues about the universe's earliest moments. Additionally, ground-based observatories like the Simons Observatory in Chile are gearing up to complement space missions, using advanced detectors to study the faint signals from the early universe. Another exciting area of research is the development of gravitational wave detectors, such as the proposed space-based LISA mission. These instruments could potentially detect primordial gravitational waves, ripples in space-time created during inflation, providing direct evidence of this rapid expansion. Meanwhile, particle accelerators like the Large Hadron Collider are probing the fundamental forces and particles that dominated the universe's first moments, offering insights into the physical conditions that drove inflation. Collaborative efforts across these fields are also fostering a deeper understanding of dark energy and dark matter, which continue to shape the universe's evolution. As we peer into the future, international partnerships and interdisciplinary approaches are unlocking new possibilities, pushing the boundaries of our knowledge. These missions not only aim to test existing theories, but also to uncover surprises that could redefine our understanding of the cosmos. With each technological leap, we move closer to answering some of the most profound questions about the universe's origins and destiny, reminding us that the journey of discovery is far from over. As we bring this journey to a close, it's incredible to reflect on how these 25 discoveries have reshaped our understanding of the universe's beginnings. From the cosmic microwave background, which serves as a snapshot of the early universe, to the groundbreaking theory of cosmic inflation that explains the universe's rapid expansion, each revelation has brought us closer to unraveling the mysteries of the Big Bang. We've explored how the abundance of light elements, the flatness of the universe, and the detection of dark energy and dark matter all point to the profound accuracy of these theories. The discovery of gravitational waves and the quest to detect primordial ripples in space-time have opened up entirely new ways to study the cosmos, while missions like the Planck satellite and the James Webb Space Telescope continue to refine our knowledge with unprecedented precision. Each of these milestones not only confirms the Big Bang theory, but also deepens our curiosity about the universe's ultimate fate and its vast, often incomprehensible scale. These discoveries remind us that the universe is full of wonders waiting to be uncovered, and that science is a journey of endless exploration. So, what other cosmic secrets are waiting to be revealed? Could the multiverse hypothesis one day be proven, or will we uncover entirely new phenomena that challenge our current understanding? The universe is vast and the questions are endless. If you've enjoyed this journey through space and time, don't forget to share your thoughts in the comments below. Subscribe for more space mysteries and hit the notification bell so you never miss an update. The cosmos is calling. Let's keep exploring together.